Hey there, it's time to do our gas laws review. So I'm going to kind of scoot along here. I'm going to skip to the things that we learned last year, but if you want to write this stuff down, feel free to pause it and write it down before we go over it next class. Super simple stuff, like here's just converting between units, which you guys already know how to do. Okay. So a couple of things that we learned last year that we're doing again this year, like Boyles Law, Charles Law, Avogadro's Law, and the ideal gas law. Boyles Law is the one that is relationship between pressure and volume. What a lot of people don't realize is that whatever the pressure times the volume equals the same answer every single time, as long as the other things are kept constant. So if the temperature and the pressure if the temperature and the moles are kept the same, then you always get the same value when you multiply pressure and volume together. So we have this really simple question here. This is sort of like what you're doing last year, where a gas has a pressure of at a volume of, and you can plug those in for P1 and V1. What will be the new pressure when the new pressure is increased to 3.9? So you know P2, solve for the new volume. See right here, what volume? And then it says the temperature is constant, so T1 is equal to T2, so they would cancel each other out of the problem if you tried to throw that into an equation. So in this scenario, it's just simple math, but we don't often think about it from a lab perspective. Like, here's a discrete, at these 2 points, at this third point, what is the volume, given this data? So what I've done is I've actually taken this question and applied it to actual data. So I took the 1.3 and the 27 for the volume, multiplied them together, and I got the constant. Actually, these two values are backwards, and that... Oh, no, they're not backwards. Sorry. This is the pressure, this is the volume, this is the constant, this is the pressure, and then this is the inverse of volume. Let me zoom in on that so it's easier to see. So I took Excel and I ran this equation through a whole series of pressure times volume equals K, pressure times volume equals K, pressure times volume equals K, pressure times volume equals K. This is assuming that temperature and moles are not changed. And so you have the whole gamut of all of them there. So let's see, we did 1.3 times 27 is equal to K. So 3.9 times what should be equal to K? Well, here it is down at the bottom. 3.9? Yep, might have just gone off the screen. Oh, there it is. 3.9 times 9 is equal to K. So they're all equal to the same constant. Well, if you graph that first set of data, if you graph these two columns against each other, you get this. You have a slow decrease in one as the other is increasing, and that's decrease versus increasing. So as the one is going up, the other is going down, or vice versa. In this case, as the pressure is going down, the volume's going up. As those things are changing, we can see this curve, and that curve is not linear. It's an inverse curve. So I even, using Excel, found the value of that curve. It's pretty close. Shockingly, look, 35.1 is the constant that makes those two things equal. What a surprise. But that is 35.1 times the inverse of x, x being these values down here, x being the pressures. So as the pressure, this is the pressure axis, changes, we get the volume. It would be a much better idea to instead graph pressure versus the inverse of volume. Why is that better? Because look at this data. It is linear, unlike the line I just tried to draw. It is nice and linear. Here, I can do that. Show off my mad techniques here. Ooh, look at that. Perfectly linear. So using linear regression, we can get an equation for it This thing is practically, man, look how close that is equal to 0. Why is that getting closer and closer to 0? Well, pressure times the inverse of pressure times volume equals a constant. As the pressure approaches 0, the volume should equal infinity, or if the volume equals 0, the pressure should equal infinity. They should be almost polar opposites of each other. This is kind of a little weird question here. So it's not quite going to 0. That actually kind of helps us later on. We're talking about what real gases versus ideal gases do. It should be going to 0, but it's not quite. There we go. It's just graphing of actual lab data, and we need to do a better job about thinking about how these questions could all be done in terms of labs. I graphed the pressure times the volume. Oh, and to make the other graph, I took the inverse of this. So I took 1 and divided it by 27, so I could get all of the inverse volume. So I have the pressure times the inverse of the volume for the second graph. So Charles' law, Sir Charles. Charles' law is about volume and temperature. But one of the keys that we have to remember anytime we deal with temperature, just like years past, temperature must be in Kelvin. So you want to make sure that you're adding, that's right, 273 to whatever the temperature is in Celsius to get it into Kelvin. And just like the previous example, volume divided by temperature should give you some constant value that doesn't change as long as the moles and the pressure aren't changed. As long as the moles and the pressure aren't changed, volume over temperature equals a constant value. So here's our example. We have a 30 degrees Celsius gas at 1 atmosphere, and here's the volume. What will the volume of the gas occupy at the same pressure? Same pressure, so we can actually just cross the pressures off because it's the same. So we have temperature, volume, new temperature, what's the new volume? Plug it in, make sure everything's in kelvins, we get for the volume. I graphed the data. I went through the same scenario like last time, but as I went through it, I said Kelvin temperature versus volume. So volume and volume divided by temperature, volume divided by temperature, volume divided by temperature. I got my constants, and then I used it in reverse, and I graphed it, and not surprisingly, look at the graph. Yay! The slope of the graph is the constant relationship between the two, between the volumes and the temperatures in Kelvin. Don't need to do the inverse graph for this one. The inverse graph would give you an odd slope that we don't want. We want to have a nice linear graph to represent the theta. This is actually similar to how Kelvin figured out absolute zero. He was graphing volume versus degrees Celsius, and it kept pointing back to negative 273. Every graph he did in Celsius, when he did it in Celsius, would go back at this. No, I just graphed the L backwards. He did a graph of volume versus temperature, which is the inverse of this one. And as the volume approached zero, temperature hit at what was negative 273 degrees Celsius. And it didn't matter what gas he did. Every gas he did, oh, there's the bell. I bet you were missing that at home. Every gas he did always kept coming back to this same value, negative 273. And so Kelvin realized that this relationship between volume and temperature points us out that at absolute zero volume, there is zero, the temperature is negative 273 all the time, which is where the beginnings of absolute zero came from. Avogadro's law. Avogadro is all about moles and volume. That's V over N equals V over N, same idea, that V over N equals some constant as long as the pressure and the temperature remain constant. And then I've actually worked out number one with a very common mistake. I haven't talked about mistakes much at all. Let's look at this question. You have 5 liter sample, 5.2 liters. You have 0.436 moles of gas, blah, 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 blah. 1.27 moles of gas, blah, 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 same temperature. What's the volume? And so a lot of people, let me just move these things out of the way here for a second. A lot of people work it out like this, and they're doing it wrong. But it feels like they're doing it right, because they see I've got this volume, moles, and that volume, but they've got to read the words very carefully. Look right here. Click the right buttons here. We add an additional 1.27 moles. So this 0.436 has an additional 1.27 moles added to it. So this shouldn't be 1.27 moles. This should be the two combined together, which is 1.70, which of course changes the volume. So those are the two correct things that should be in there. This is just me saying read the words carefully. Okay? Thank you. And then we have the ideal gas law. The ideal gas law, PV equals nRT. We have the relationship between pressure, volume, moles, and temperature. I actually find this one kind of fascinating. I don't know who figured this out, but if you take any sample of gas, you do pressure times volume over NT. These are the four variables we manipulate. It equals a constant, just like before. Equals a constant. Equals a constant, right? Equals a constant, see? And so what they do is they take all these laws and put them together. PV over NT equals a constant, and we call that constant the gas law constant for R. Look at me, I just changed that K into an R. That was fascinating. Now, you can measure pressure in atmospheres, kilopascals, torrs, a bunch of things. So that would impact the answer for R. Volume is typically measured in liters, maybe milliliters, maybe cubic decimeters, but primarily liters, and so let's try to focus there. N is always moles, and temperature must always be Kelvin. But dependent on which units you use, atmospheres, kilopascals, why is there a J there? We'll get to that in a second. It impacts the answer. So this is in atmospheres, and we have our standard 0.0821 for R. This one's in kilopascals, 8.31. And then this one is in joules, which is actually also kilopascals. Man, the one for torr is missing there. Let me find something. I'll be right back. Ooh, I hope you didn't miss me. I've been gone for a while from my perspective. From your perspective, it's probably just a blink of an eye. So I looked at the equation sheet. Here it is. I looked up the equation sheet and found the other value for R. You can see that the real deal with this one is that it has torr in it instead of kilopascals or atmospheres. So if you were given torr, what's the other unit that torr can be replaced with? Millimeters of mercury. If you're given torr or there's the bell again. If you're given torr or millimeters of mercury, you can use 62.36. Of course, if you want to change the units, you can, or you can change R's. So, you have several choices of R here. I feel like there's a pirate joke coming, but I just can't come up with one on the fly. Sorry. We'll get along here in a minute. So, here we go. Let's read this question and stop mumbling. We have moles, temperature, volume. Temperature's in the wrong units. Change it to Kelvin. There we go. Boom. Now it's in Kelvin. That's already in liters. That's in moles. So what pressure does it doesn't actually say what units. I picked the atmosphere. That's my favorite unit. That's the one I like to hang out with on the weekends when I'm doing pressures. So I worked this out in atmospheres, but since it doesn't actually specify the units, you could have your answer coming out in kilopascals or torrs or millimeters of mercury. But if you do that, that alters the R value, which alters this answer here. But there I am. I just worked out the pressure in atmospheres. Pretty boring, pretty standard stuff. Yeah. Then lastly, up there in the top right, this is typically called the combined gas law. This right here, PV over T equals PV over T. It's really not the all combined gas law. That's this one here, my a beautiful handwriting, PV over NT equals PV over NT, and they both equal R, which is a constant. That's really the only gas law worth knowing, is PV over NT equals R. You can read any problem and use that. A sample of methane gas at this, what volume, this pressure is increased to 1.52, not increased by, but to. So it is actually 1.52 afterwards, and the temperature's increased to 11 degrees Celsius. The moles aren't changing, so N1 and N2 are both the same, so you can just cross those off, but they could have been in there. So that's a good example. And you just solve for the missing volume. So make sure to know your gas laws. Again, though, if you know PV over NT equals R, you know every gas law. What do you mean I know every gas law? Well, I'll tell you. You know V over T, great. You got P over V equals R. You've got V over N. You've even got, whoa, what is this guy? P over T. What is P over T? It's Gius X. And then N over T equals, that's probably a gas law too. I don't know the name of that one. We'll call that one, I don't know. That's a NT law, I guess. Let's see, what else is in the notes that we're not doing right now? Molar mass, gas stoichiometry with at STP, or longer problems, some little gas law stoichiometry problems, so you can just jot down answers here if you want. Or, here we go, here's a reaction, pretty simple. Oh, it's actually not simple, it's a limiting excess reactant problem that you have to take the smaller answer to use in your ideal gas law problem. Here's a new one. We're going to talk about this one in class tomorrow. Molar mass equals dRT over P. Dalton's law of partial pressure is so simple and yet so complicated. So we're going to get in Dalton's law of partial pressure a bunch tomorrow, and how quite often with Dalton's law of partial pressure there can be two, there's a line missing right there. There can be two completely different approaches to the problem and still get you the same answer. Here's one with mole fraction, which we haven't done yet, so that's interesting. And another one with mole fraction, which is going to be new to you. We're going to talk about kinetic molecular theory a bunch, and we're going to talk about Max Boltzmann's probability distribution functions. That's my horrible drawing. This is a beautiful drawing. It's not in the notes, but it is still glorious. And then also talk about effusion and diffusion. And we're going to talk about real gases and how real gases are a little bit more difficult to work with than these ideal gases in terms of the math. So here we are doing some math to solve for these two equations. And we're talking about deviations from the ideal gas law, and even talk about labs that could be done using all this stuff. Alright guys, so study your basic gas law stuff. Make sure you know PV equals nRT, V over T or V over T, PV equals PV, V over N equals V over N, and then how to convert from kilopascals to atmospheres to millimeters of mercury to the one I've forgotten off the top of my head. Did I say torricelli's yet? Everyone loves a good torr. Yeah, torricelli's. Alright, have a good night. Goodbye.